during a high-level military exercise designed to test the readiness and interoperability of modern combat units. One of the primary battle tanks experienced a sudden and complete engine failure. This tank, equipped with the latest in digital control systems and hybrid mechanical technologies, was a centerpiece in the exercise scenario. The failure occurred during a coordinated maneuver, which immediately disrupted the formation and triggered a halt in operations. Engineers from the on-site support team were dispatched promptly. These individuals were trained in the technical systems of the tank and equipped with diagnostic tools built to read error codes, assess software irregularities, and perform remote engine interface scans. Initial readings revealed no standard faults. The primary digital control unit reported all systems nominal. The fuel pressure systems, electrical routing, battery supply, and exhaust systems showed normal metrics. Despite this, the engine remained unresponsive. Several attempts to initiate an emergency start sequence failed. The engineering team began to suspect a deeper issue within the integrated propulsion system. The tank model in question used a next-generation hybrid turbo-diesel engine with electric assist and internal smart regulation. While powerful and efficient, it was also known for being particularly difficult to repair in the field without full access to the maintenance depot database. As the minutes turned into hours, the Tactical Command Center faced increasing pressure. The halted exercise was bleeding resources. Fuel trucks were on standby, air support was circling for no reason, and infantry units had to be repositioned. Each passing moment cost not just money, but also operational rhythm, morale, and the flow of mission objectives. Multiple engineers rotated shifts, trying different calibration combinations. Some tried to reset the engine control module, others adjusted the electronic throttle input range. None of it worked. The tank's internal computer continued to report that the system was functional, yet there was no response to manual input or remote activation. The chain of command was alerted that a critical failure had stalled the exercise, and a call was made up the ladder to the battalion-level leadership. With each passing report, the urgency of the situation escalated. Commanders requested escalation to manufacturer-level support. Remote technical experts attempted to walk the on-site team through deeper system logs and binary outputs. Still, no progress was made. A small group within the engineering unit began to suggest disassembling parts of the engine manually. Though this was considered risky and time-consuming under exercise conditions, logistics officers warned that any such disassembly could void testing parameters or delay certification of the unit's readiness. As the exercise crossed the third hour of interruption, the stress levels peaked. The tank was not just a machine, it represented billions in defense investment and a critical piece in military strategy. The reputation of the systems integrators, the engineering team, and even the officers overseeing the test was being called into question. Senior leadership within the armored division began to evaluate options beyond the standard technical procedures. There was recognition that despite all the modern systems and diagnostics, the human factor, the experience and intuition that older veterans carried, was completely missing from the situation. A field decision was made to document the full failure report and consider pulling the tank from the exercise entirely. This would cause ripple effects across the simulation, forcing a redesign of the remaining drills. However, before that decision could be finalized, a seasoned colonel suggested an alternative. The colonel referenced an Army veteran who had decades of experience working on armored vehicles. This individual, though long retired, had served as a lead technician in multiple combat zones and had developed a reputation for solving issues no textbook or schematic could explain. Although unconventional, the general officer overseeing the drill approved contacting the veteran. Time was running out and standard solutions had failed. The call was made not as a formality, but as a last attempt to salvage the situation. The incident was logged as a classified mechanical stand-down with engineering override pending. While the veteran had no direct access to the latest digital manuals, he had a background that predated most of the onboard systems. He was known for solving problems with a deep understanding of mechanical-electrical interplay rather than relying on software feedback. This single point of failure exposed an underlying issue in the military's modern doctrine, an over-reliance on technology without contingency for system-wide sensor failure. The diagnostic tools failed because they were programmed only to detect what they were told to look for. The tank's onboard intelligence could not comprehend the possibility of a non-digital problem affecting a digital system. That gap rendered every line of code and every sensor output useless. It took an extraordinary chain of events and a crisis in command confidence to force a reconsideration of how mechanical failure should be approached. In hindsight, this moment became a critical lesson in military engineering circles. The exercise was eventually restructured to include fail-safe systems that incorporated manual override options. Technical training protocols were rewritten to include case studies about engine response failure without software alerts. The data gathered during the tank malfunction was used to build simulation models for identifying similar blind spots in other vehicles. Although the tank was returned to operational status through external assistance, the implications reached far beyond a single exercise. The reputation of the engineering team remained intact due to their transparent documentation and collaboration. The manufacturers initiated a review into the embedded firmware logic responsible for misreporting system status. New guidelines were introduced for balancing AI diagnostics with human mechanical assessment. The cost of the delay, while significant, paled in comparison to the long-term value of the incident's lessons. What began as a mechanical breakdown became a catalyst for rethinking the relationship between man and machine in military operations. Despite having access to cutting-edge diagnostic tools and sophisticated software systems, the group of elite military engineers found themselves in a frustrating and embarrassing situation. The failure of the modern tank engine during a critical military exercise presented not just a mechanical problem but a serious test of professional capability, competence, and institutional credibility. Each engineer brought forward their specialized expertise, many holding advanced degrees in mechanical, electrical, or software engineering, with years of hands-on experience in defense projects. These were not ordinary field technicians but top-tier experts representing major defense contractors selected specifically for high-stakes situations. However, their collective efforts yielded no solution, and time was working against them. Initially, the engineers approached the issue with standard procedures. They connected advanced diagnostic computers to the tank's control systems. These diagnostics were supposed to detect anomalies, malfunctions, or system breakdowns across the mechanical-electrical interface. The expectation was that the engine control unit, ECU, would display error codes or alerts, guiding them toward the fault. However, the system displayed normal operational status across all critical areas: fuel injection, combustion timing, hybrid synchronization, battery output, and software configurations. Everything checked out on the surface, yet the engine remained non-functional. This contradiction between digital feedback and physical reality set the tone for escalating confusion. Believing that the error was rooted in the software, one group of engineers attempted firmware reinstallation. They accessed the ECU to rewrite the operating system parameters, hoping that a corrupted line of code was preventing ignition. The update process went smoothly, but the result was the same. The tank's startup sequence remained non-responsive. Another team hypothesized a failure in the sensor network. They began replacing critical sensors: oxygen, throttle position, temperature, pressure regulators, and crankshaft angle detectors. Each sensor was removed, tested, and replaced with verified spares. Still, no change. The diagnostic system continued to report optimal performance. Yet the engine, the heart of the tank, was lifeless. The engineers' frustration grew with each failed attempt. Communication between team members began to shift from confident collaboration to subtle blame shifting. Some questioned whether the tank's control software was properly calibrated for the latest firmware. Others suspected electromagnetic interference from nearby communication systems. Every theory led to more confusion. Requests were made for additional technical manuals and schematic breakdowns. Emails were sent to engineers back at the manufacturing facility. Remote support teams from overseas joined via secure channels to interpret live data and provide advanced guidance. Still, all the theory, analysis, and expertise resulted in no practical solution. Embarrassment soon followed the frustration. What started as a technical challenge had now become a reputational crisis. Senior military officials were observing the failure unfold with growing concern. These officials had authorized billions of dollars in contracts to develop and field these modern tanks, sold on the premise of reliability, battlefield resilience, and ease of maintenance. The fact that a team of elite engineers could not revive a single tank engine shook confidence in the program. This wasn't a failure that could be hidden or quietly corrected. It was happening in real time during a major exercise with full visibility across multiple branches of the armed forces. The incident triggered concerns beyond the technical. Military leadership began questioning whether the entire doctrine of digital-first repair had flaws. The scenario demonstrated a systemic vulnerability. The engineers relied entirely on the digital system to diagnose the issue, but the system itself failed to recognize the malfunction. With every sensor reading as normal, the very logic of their troubleshooting model collapsed. Engineers were trained to follow data, but in this case, the data betrayed them. As more hours passed, engineers tried unconventional methods such as hard system resets, bypassing digital ignition relays, and even rolling back software updates to a legacy version used in earlier models. Nothing worked. Each attempt that ended in failure reduced morale. The chain of command began expressing dissatisfaction through formal channels. Field reports were logged with statements like "engineering impasse continues" and "unable to determine fault origin." Contractors involved in the tank's development received urgent communications requesting additional support or escalation pathways. Some of the engineers, despite their professional poise, began to feel the psychological weight of failure. The pressure of being watched, judged, and possibly held accountable for an unsolved issue during a mission-critical scenario created an environment where rational troubleshooting began to falter under emotional strain. The breakdown in trust between the engineering teams and the command structure was subtle but unmistakable. Officers who once deferred to the engineers began questioning their methods, asking why a basic combustion engine could not be started, despite all the resources available. Engineers, in turn, grew defensive, explaining that without accurate feedback from the system, no logical path forward existed. The gap between theoretical knowledge and practical problem-solving became painfully clear. This created internal conflict, as some engineers pushed for exploratory disassembly of the tank's systems, risking damage and chain of custody complications, while others argued for halting further action until external specialists could be brought in. Contractors faced the embarrassment of being unable to defend their technology. The tank was supposed to be battlefield-ready under extreme conditions, yet failed during a controlled drill. Journalists were not present, but word of the incident spread within the defense community, damaging the brand image of those involved. Discussions began about how to prevent similar issues in the future, including the need to integrate analog override options, simplify sensor dependencies, or even bring in older generation mechanics during training to balance out the hyper-specialization of modern technical staff. One of the most frustrating elements was the realization that the engine itself was likely not damaged. All indications pointed to a blockage or misconfiguration that was beyond the perception of the software. The inability to cross-verify digital readings with mechanical insight proved to be the engineering team's blind spot. They had trained extensively on computer-driven problem-solving, but had little practical experience dealing with systems where data misrepresents function. It became increasingly clear that the software lacked the capacity to recognize every possible failure mode, and the engineers lacked a fallback methodology for operating without digital guidance. This frustration and embarrassment were compounded by the high expectations placed on the team. These individuals were hailed as the best and brightest, and the failure to fix a single tank engine raised questions about the entire framework of modern military engineering. Trust in automated systems, training protocols, and even recruitment strategies came under scrutiny. Some commanders questioned whether the military had moved too far away from hands-on mechanical knowledge in favor of digital abstraction. The incident highlighted a critical need for balance between software-driven operations and the practical intuition that only years of physical system interaction can develop. The failure of the tank engine and the inability of top engineers to resolve the issue led to an escalation that moved beyond the realm of standard technical protocols. With each passing hour, pressure mounted on the military leadership to find a solution that would restore operational continuity and confidence in the military's technological infrastructure. Reports from the Exercise Command Center detailed the repeated failures of diagnostics, software patches, sensor replacements, and hardware inspections. Each failed solution was carefully logged, and the cumulative evidence pointed to a larger, systemic issue. At this point, the commanding general overseeing the exercise faced not just a technical dilemma, but a crisis of credibility. The decision to proceed beyond traditional solutions required a bold and unconventional move. It was under this immense operational pressure that the general made a decision that many in the room found unusual, even radical. The general, a seasoned leader with decades of battlefield command experience, recalled a retired Army veteran, whose reputation in mechanical problem-solving was legendary within armored units. This veteran, known informally among his peers as the Tank Whisperer, had served multiple combat tours and had worked extensively on earlier and transitional models of tanks, during times when software was not the primary diagnostic tool. His ability to detect problems through experience, intuition, and mechanical sensitivity had earned him awards, commendations, and the informal admiration of both enlisted personnel and officers. Despite having retired years earlier, his name still surfaced occasionally in conversations about critical field repairs that no one else could perform. The general had served alongside him in earlier campaigns and knew firsthand his unconventional genius. The decision to reach out to this veteran was not taken lightly. Standard operating procedures typically discouraged relying on retired personnel during active operations. However, the present circumstances had surpassed normal boundaries. The general bypassed layers of bureaucracy, contacted the veteran directly, and provided him with a classified summary of the engine malfunction and the failed repair attempts. The veteran listened calmly, asked a few questions, and agreed to assist without hesitation. Within the chain of command, this decision raised eyebrows. Some questioned the optics of calling in a retiree to solve what cutting-edge professionals could not. Others were concerned about security clearance, liability, and the potential undermining of institutional credibility. The general, however, made it clear that the objective was operational resolution, not ego preservation or procedural formality. The veteran's background gave him an edge that no modern engineer could replicate. He had begun his career working on tanks when much of their operation depended on manual calibration, analog gauges, and physical manipulation of components. Over the years, he had transitioned through the technological evolution of armored vehicles, from hydraulic systems to digitized interfaces. However, he never let go of the fundamentals, understanding how sound, temperature, pressure, vibration, and even smell could reveal things that no sensor could capture. His success was not derived from any secret method, but from decades of direct, real-world exposure to countless mechanical systems under varied conditions. His reputation was built on results, and his nickname came from a string of field miracles that often saved missions from total failure. When the general made the call, it was not simply to fix a tank. It was an appeal to wisdom and deep domain, intuition that no training manual could teach. The veteran had solved similar issues before where software failed to detect non-digital faults. His insight was not clouded by dependency on computers or dashboards. He relied on the synergy between human senses and mechanical patterns. This made him a rare breed in a world increasingly dominated by algorithms and data feeds. His career had often been at odds with conventional protocol, yet his results had always silenced critics. His presence in the current crisis served as a reminder that experience and adaptability remain unmatched tools in high-pressure environments. The general's decision also signified a larger problem within the institutional hierarchy, the assumption that newer is always better. The tank that had failed represented the peak of military technology, but that technology had failed under stress. The engineers, brilliant in their own right, were trained to follow digital logic. When the logic failed, so did their framework for action. The general saw what others missed, the need to integrate diverse forms of knowledge, including the lived experience of veterans who had learned to adapt without digital crutches. Calling the veteran was not just an act of desperation. It was a recalibration of priorities, valuing practicality over prestige, outcomes over optics. The arrival of the veteran was met with mixed reactions. While some engineers welcomed the additional help, others saw it as an implicit indictment of their failure. The general addressed the team directly, framing the veterans' involvement not as a criticism but as a strategic resource utilization. He reminded everyone that military effectiveness depends on leveraging every available asset, especially those capable of solving problems outside the scope of standard procedure. This reframing helped ease tensions and allowed collaboration to resume under a new mindset. The veteran was granted full access to the tank's systems, and while he chose to bypass most of the software interfaces, he carefully reviewed the engineer's reports and examined the physical structure with practice familiarity. The general's gamble paid off, not only in technical success, but in setting a precedent for leadership under uncertainty. By turning to someone outside the active duty structure, he demonstrated that wisdom and history still hold irreplaceable value. The decision sparked internal discussions about expanding roles for retired experts. As emergency consultants in high-tech failure scenarios, proposals emerged to integrate veterans into training simulations and include their case studies in military engineering curricula. The general received both praise and scrutiny for his decision, but the ultimate outcome validated his leadership. He prioritized mission success and operational learning over hierarchy, and that made all the difference. The moment also shifted the internal culture of the unit. Engineers began to appreciate that problem-solving requires both data and depth of understanding, and that sometimes the solution lies not in better code but in broader perspective. The incident became a case study in military leadership programs. It highlighted the need for adaptable thinking, intergenerational knowledge exchange, and the courage to make unconventional decisions under pressure. The general's call to the veteran became more than a crisis response. It became a symbol of respect for experience, a demonstration of humility and leadership, and a proof that old-school expertise still has a role in a high-tech battlefield. Upon arriving at the site, the veteran immediately dismissed the reliance on diagnostics and software logs. He began by conducting a physical inspection of the engine housing, noting heat patterns, oil residue, and slight irregularities in the casing bolts. His method focused not on digital readings but on the subtle mechanical cues that indicated a deeper issue. He tapped into his years of experience dealing with similar engines, both legacy and transitional models, and quickly ruled out electrical failure due to the consistent response in sensor readings. While engineers had spent hours focusing on sensor arrays and computer reboots, the veteran directed his attention to a fundamental component often overlooked in digital diagnostics: the manual pressure regulation valve and its corresponding torque control assembly. Using basic hand tools, he accessed a component known to him as a potential point of misalignment in hybrid turbodiesel systems. This component controlled the transition between electric assist and diesel ignition at startup, and though it was electronically regulated, its physical alignment could be compromised through subtle thermal expansion, improper calibration during previous servicing, or slight impact vibration. He removed the panel securing the hydraulic manifold, examined the actuator manually, and noticed that the mechanical torque alignment was off by less than a degree, an amount negligible to sensors, but enough to prevent mechanical engagement. This misalignment was not a fault the software could detect because the sensors reported electrical connection and position as functional. The failure was mechanical in nature but hidden within an electronically reported system. He then manually disengaged the actuator, adjusted the torque cam, realigned the manual override valve, and locked it in place. He followed this by opening the primary pressure vent manually to purge trapped air and reset hydraulic balance. The action took less than 10 minutes, but was rooted in decades of experience and knowledge of systemic weak points not documented in current manuals. These minor adjustments resolved a mechanical interlock that had prevented the fuel compression cycle from triggering the ignition sequence. The engine was now mechanically capable of engaging. He signaled the engineers to attempt startup without altering any software or rerunning diagnostics. When they did, the engine started immediately, producing a steady rumble and responding to throttle input without hesitation. The engineering team, shocked by the result, began documenting every movement the veteran had made. They ran a post-repair diagnostic to confirm system stability and found all readings within operational range, matching baseline parameters without any software flags or anomalies. The veteran explained that this particular misalignment had existed in earlier iterations of the engine model, but had been considered so rare that it was excluded from later digital error reporting. He had seen it multiple times during live deployment in varying climate zones where expansion and contraction of metal components caused tolerance shifts. In those earlier models, manual inspection was standard practice. However, with increased reliance on sensor-fed data, manual verification had fallen out of regular protocol. As a result, newer engineers lacked the exposure to detect such a subtle mechanical disruption. The repair prompted an immediate debrief among military leadership and engineering supervisors. The veteran provided a full verbal breakdown of the problem and outlined steps to identify and prevent future occurrences. He highlighted the gap between sensor-reported data and real-world mechanical behavior, arguing for the reintroduction of physical verification steps into routine diagnostics. He recommended adjustments to training programs that included hybridized troubleshooting combining manual inspection with software reliance. His approach was pragmatic and data-informed but rooted in tactile feedback and physical intuition. He suggested incorporating analog fallback options in future engine designs, allowing a physical reset or adjustment pathway independent of software control. The general overseeing the operation ordered a full documentation of the incident and initiated a report to higher command summarizing the procedural changes needed based on this experience. Defense contractors were instructed to review their diagnostic frameworks and consider updates that would include flagging conditions that did not fall within binary error categories. The incident was escalated to the Doctrine Review Board, where a technical team began evaluating how to reintroduce mechanical failsafe knowledge into both the design and repair processes for advanced combat systems. The engineering schools associated with the defense sector were also informed, and a memo was distributed recommending the creation of hybrid training modules. The event shifted the mindset across multiple departments. Engineers realized that even with flawless sensor systems and digital readouts, there remained a category of issues that only human experience could address. Several engineers on the team requested mentorship sessions with the veteran, eager to learn the tactile methods. He employed and understand the limitations of software dependency. Within a few weeks, internal workshops were developed, and the veteran was invited to serve as a consultant for engineering training, with special focus on legacy-to-modern systems integration. His repair was not merely a fix but a demonstration of a deeper principle. When digital systems fail to capture the nuance of physical misalignment, only seasoned human expertise can bridge the gap. The military's Equipment Reliability Board opened an inquiry into how many similar tanks might carry the same vulnerability. Field units were instructed to manually inspect the torque valve alignment as a precaution, and in several cases, minor deviations were found and corrected before failure could occur. These preemptive corrections validated the veteran's assessment and underscored the systemic nature of the issue. Contractors began redesigning parts of the valve structure to include real-time, analog alignment indicators visible without full disassembly. These changes were submitted for review and integrated into the next manufacturing cycle. A field bulletin was issued with updated inspection procedures and a list of manual override scenarios for engineering teams in both domestic and forward operating units. The effectiveness of the repair also had cultural ramifications. Within the engineering unit, there was a renewed respect for manual skills and a collective reevaluation of the belief that technology alone could address all operational problems. The commanding general used the incident as a teaching moment, holding a formal address about the balance between technology and human expertise. He emphasized that future readiness depended on cross-generational knowledge and the humility to seek solutions from any qualified source, regardless of title or status. The veteran, once a retired name in a long personnel file, was now seen as a living resource, a repository of knowledge that the military had nearly lost to time. This single repair evolved into a structural learning moment. Defense departments reevaluated their contractor relationships, insisting on blended training that included real-world scenarios where software alone could not resolve issues. Funding was allocated to develop mechanical-digital diagnostic fusion, tools capable of cross-validating sensor input with physical system behavior. Meanwhile, the veteran continued contributing as a specialist, shaping the future of training, maintenance, and mechanical intuition in a military increasingly dominated by code and automation. His legacy now extended beyond past campaigns into shaping a resilient, adaptive future built not just on innovation but also on the irreplaceable value of human expertise. The resolution of the tank engine failure sparked an immediate and widespread debate within military leadership and technical command structures regarding the increasing over-reliance on software, automation, and sensor-based diagnostics in critical military equipment. Reports documenting the incident were circulated rapidly through defense channels, highlighting how a team of highly trained engineers armed with advanced diagnostic systems failed to identify or resolve the issue, while a RETI/RED veteran without access to the latest software tools managed to solve the problem using manual inspection and intuitive expertise. This stark contrast forced military officials to reevaluate the assumption that digital systems could fully replace human experience in high-pressure, real-world scenarios. Strategic briefings following the exercise emphasized the incident as a case study in operational risk caused by one-dimensional dependency on automated systems. Analysts within the defense infrastructure pointed out that military hardware had undergone massive digital transformation over the past 2 decades. But training and operational doctrine had failed to evolve in parallel with regard to failure response under digital blind spots. A consensus began to form that digital systems, while efficient under normal operating parameters, lacked the adaptability to detect non-coded anomalies or physical misalignments that fell outside programmed error ranges. This limitation, previously considered statistically insignificant, had now proven capable of halting a major operation and jeopardizing mission continuity. Senior defense engineers and commanders began convening to discuss structural adjustments in training and doctrine. Think tanks and advisory panels conducted rapid assessments of diagnostic systems in current and upcoming platforms. The findings were consistent across models. Modern tanks, jets, naval vessels, and missile systems all operated on the presumption that their self-diagnostic modules could identify any critical failure in real time. The failure during the exercise exposed a fundamental flaw: self-reporting systems only flag errors they are coded to recognize. If the root problem lies outside those parameters, the system either reports no fault or misattributes the issue, leading technicians into a loop of ineffective troubleshooting. This realization forced the Joint Systems Reliability Division to open a formal inquiry. Subcommittees were assigned to determine how knowledge from older systems and historical repair techniques could be reintroduced into current engineering. Education. Preliminary proposals were drafted recommending that training programs for new defense engineers include modules dedicated to analog system interpretation, mechanical intuition development, and legacy system cross-training. The incident became a catalyst for acknowledging that technological sophistication must be accompanied by human wisdom, especially when it comes to system irregularities that do not fit algorithmic expectations. The general who authorized the veterans' involvement submitted a strategic briefing to the Department of Defense highlighting several key points. First, the efficiency of military operations depends not only on cutting-edge technology, but also on a robust repository of experience that spans multiple generations of hardware. Second, failure to integrate experienced veterans into the training and diagnostic chain poses a risk to operational resilience. Third, budgetary constraints and modernization efforts must not result in the exclusion of practical knowledge that has proven its value repeatedly in the field. Fourth, doctrine must be adapted to reflect hybrid solutions combining digital and manual methodologies. Following this, a policy proposal was introduced to establish a defense engineering heritage program designed to identify and recruit retired veterans with high mechanical aptitude and extensive field experience for part-time, instructional and consulting roles. The program would not only preserve institutional knowledge but also actively apply it to support ongoing operations and design improvements. A secondary objective included compiling a digital archive of veteran problem-solving methods, accessible to active duty engineers and used as case studies and troubleshooting exercises. These resources would include video breakdowns, procedural guides, and real-time mentorship via secure communication platforms. Military academies and engineering schools began integrating these changes into their curricula. Admission requirements and qualification tracks were updated to reflect not only technical ability but also problem-solving versatility. Training modules were restructured to simulate diagnostic failures where software tools provide no assistance, requiring students to identify and correct mechanical faults using observation, logic, and physical feedback. Instructors encouraged open-ended analysis rather than checklist-based inspections, cultivating adaptability and creative thinking. Simulation drills began to incorporate aging hardware with unpredictable behavior to reinforce real-world uncertainty and complexity. This movement toward experience integration also had an effect on procurement and design policy. Equipment manufacturers were encouraged to include mechanical fallback mechanisms and analog indicators in systems that previously relied exclusively on software interfaces. New contracts included clauses mandating field serviceability under partial or complete digital system failure. Interface designs were reviewed to ensure accessibility for physical inspection without complete system teardown. Veteran consultants participated in design reviews, offering insights into operational challenges and recommending practical design adjustments that younger engineers might not anticipate. Within 6 months of the incident, several units across the Army, Navy, and Air Force initiated pilot programs to embed experienced veterans within their maintenance and engineering corps. These veterans served not as replacements for modern engineers but as complements offering contextual understanding and first principles analysis in addition to modern theory. Reports from these pilot programs showed a measurable increase in repair speed, reduced reliance on external technical support, and improved morale among junior engineers who valued the mentorship and grounded perspective. The recognition of the veteran who fixed the tank engine went beyond symbolic appreciation. He was awarded a formal commendation, and his methodology was cited in multiple internal publications as a gold standard for adaptive field repair. Defense journals published case studies on the event, analyzing how the synthesis of experience and intuition outperformed automated systems under specific conditions. Military leadership used the incident as a communication tool to reinforce the importance of humility, continuous learning, and cross-generational collaboration within technical teams. The broader cultural shift initiated by this event marked a turning point in how the military approached technology, training, and preparedness. It rejected the idea that innovation alone guarantees superiority, emphasizing instead the integration of legacy wisdom with emerging capabilities. Officers began emphasizing hybrid thinking in command briefings, Tactical field units conducted internal seminars on historical maintenance practices. Procurement teams began requesting veteran feedback during field testing phases. Young recruits were encouraged to study not only their digital systems, but also the physical principles underlying mechanical function. Budget allocations were modified to support these initiatives. Funding was set aside for legacy equipment libraries, mechanical training facilities, and veteran instructor honorariums. Partnerships were established between the military and veteran organizations to create pathways for skilled retirees to return in teaching capacities. Engineering conferences began including panels on experiential knowledge and non-digital failure modes. Defense strategy documents incorporated language, recognizing the role of veteran insight in ensuring operational continuity under stress. Ultimately, the incident changed not just how problems were solved, but how they were anticipated. The military adopted a layered approach to reliability, blending digital precision with analog resilience. It embraced the truth that while machines evolve, the human capacity to interpret, adapt, and innovate remains constant. The general's decision to call upon a retired veteran became more than a tactical move. It became a strategic lesson that reshaped defense engineering philosophy and operational culture at every level.